Hello, Mehran, are you there?
Hello.
Oh, give me a second. Okay. Can you hear me now?
Yeah.
Okay, perfect. I was changing that. Okay. So Carl, I sent you an email before. I don't know if you've seen it. So unfortunately today I'll have to leave a bit earlier. So usually the whole TMB session, we have like the presentation. In this case, going to be by you. And then after that, some Q&A and discussion with Carl. But I'm gonna have to leave like around a bit, maybe 4, something like that. So maybe it's gonna be like in between the Q&A, I expect, something like that.
Well, we've already discussed this. I also have to leave at 4 for a meeting with Francois Chollet.
Oh, really? Okay.
Yeah.
Then it's perfect. Okay. Then I don't have to leave early. Okay, nice.
And also, Mehran's actually in Melbourne, so it's the middle of the night for him. So
Okay, so everyone has to leave early today. That's perfect. Okay,
No,
nice.
from my side, I appreciate every minute I get out of these meetings. So even if it was gonna take longer, I definitely wouldn't have minded for sure. Yeah. So I am unlucky today, basically.
So I thought you were in the Dublin, or is it? I misread that.
I was in Ireland for 7 years, but then, as fate would have it, I moved just a little over the other side of the world.
Just a little, yeah.
Just a little bit, yeah.
Okay, nice.
You're in the UK now, are you?
Yes, in Brighton.
I see.
Yeah.
I haven't had the pleasure of meeting you. What's your name again?
Miguel.
Miguel. Nice to meet you, Miguel.
Yeah, I feel you've been maybe exchanging emails with Reedy, I guess.
Yes, yes.
Nice. Okay, can we do like a quick test? You can share your screens to check that everything works fine. And then I guess shortly after, well, we can start because if everyone has to leave early, maybe just make the most of it. Okay, nice. Okay, perfect. Okay, so I guess we can start now then. So today we have Mehran Bazargani, that's pronounced correctly, or probably. So he's going to be talking about modeling human perception using hierarchical generalized predictive coding. So yeah, feel free to start.
Thank you for having me. As Miguel said, today I'm going to be talking about modeling human perception using hierarchical generalized predictive coding through an online triple estimation approach. This is a collaboration with my colleague, Dr. Simon Orbas, and also my supervisors, Dr. Brandon Murphy and Dr. Adil Razi. So let me just get started. So the content of today's presentation. First, I'm going to define some basics, Bayesian brain and perception. How do they relate to one another? Generative model versus generative process. What do they mean exactly? Generalized coordinates of motion, a key component of our implementation. Variational free energy, and of course, variational Laplace. And then I'm going to jump to predictive coding and connect it to online triple estimation. When I say triple estimation, I'm talking about state inference, parameter learning, and uncertainty estimation in an online fashion. Then I'll talk about the separation of temporal scales, and I'll be introducing 2 of the schemes that we have developed for implementing the separation of temporal scales through online predictive coding. Then I'm going to be talking about a one-layer predictive coding and some experiment results And then the implications of what are the things that we need to consider when we move from a one-layer predictive coding to a two-layer predictive coding. Surprisingly, things can get a little complicated. And then I'll basically propose the questions and concerns that we have that we seek to get advice on, hence today's presentation. So some of the basics about what we're doing here. So Bayesian brain hypothesis goes back to the time of Helmholtz. So the idea is that the brain is in the game of inferring the hidden causes behind its sensations, usually formulated as a conditional probability of some hidden state X, and then given the current sensory stimuli that I'm receiving. For example, when the light hits my eyes, it generates some electrical signal in my neurons and the sensory epithelia, and then given that input signal, the brain generates some explanation as to what's the most likely cause outside in the world that could have caused this particular input. If the brain or the generative model can do this well, then we're saying that perception has occurred. So this requires having a generative model of the world. And this is basically called perception as unconscious inference. Quickly talking about generative process and generative models. On the left-hand side, we have the generative process. That is the basically the entity that is causing all the sensations that we're receiving from the world. So let's say there's some X star that is encoding the hidden states in the world, in the invisible world, in our generative process, in the generative process. Let's say we have the face of Steve Jobs there, but then the observation that we get from this world is some altered, noisy version of that truth, of that unknown truth. Let's call it Y. Now, our generative model, for example, our brain, is given that input data, that Y, and through some internal states, X, and some parameters of itself, hence basically the generative model inside the brain, let's say, it wants to infer what is the most likely cause outside beyond the skull that has caused this observation Y. Two things to note. The generative process is not directly observable and it resides beyond the skull. So this boundary through which the communication happens between things from the free energy principles perspective is called a Markov blanket. And the internal states X, let's say the synaptic weights, for example, or let's say the neuronal activity, let's say within the skull, they behave as if they're carrying information about the invisible external states X star. So that's an interesting perspective from information theory point of view, if you're interested in that particular discipline. Now let's dig a little deeper about generative model. So in a dynamic world, a generative model means that basically so it's important to define generative model. What do we mean exactly? So the generative model in a truly dynamic world has to have some belief about the dynamics of the world beyond the Markov blanket as to how the world is changing, although it is invisible, but it has to have some belief about how it's changing. So if the world is at state X, by the generative model's estimation, what does its dynamics even look like? For example, the velocity, the acceleration, the jerk, and higher temporal derivatives. In other words, the dynamics of the world, not just where it is, but how it's changing. So it is as if the generative model is in the game of chasing an ever-moving target, which makes modeling human perception in an online setting even more challenging. So the generative model also has to have a belief about how the world causes its sensations. Basically, if the world is at state X and the dynamics look like such and such, what is the most likely sensation Y that the generative model should be experiencing? So those two components together constitute a generative model. Now, This is exactly demonstrated mathematically here. The sort of first equation, x dots, which is the rate of change in the world, is defined as a differential equation. We have the deterministic component of it, that is the f function. It's a function of x, nu, and theta. I'll be talking about these three variables in detail later on, but x, you can think about it as, let's say, the neuronal activity in the brain. Fast-moving neural activity. The nus are the variables that are used to encode how different layers at different depths of the hierarchical brain or the generative model talk to each other. Without these nus, the interlayer communication cannot exist, and thetas can be looked at, described as the parameters of the generative model. These are slowly moving entities in the brain, for example. They encode, let's say, the synaptic weights. Now, omega x is just the random fluctuations that that are happening in the world, that are called, that basically that's how we introduce randomness in the world. So F is also called the flow of the state dynamics equation, the deterministic part. So also we have the second component, as I described on the left-hand side, which determines how a given state of the world would result in the observation that I'm experiencing right now. In other words, Y, which is the sensation that the generative model or the brain is receiving right now, is encoded as a function, a deterministic function G, plus, again, some random fluctuation in the observation, some noise in the observation. Could be noise in the sensorium, for example. Now, interestingly, if we assume a normal distribution over these random fluctuations, all of a sudden we move to the world of beliefs, meaning that now we can describe these two equations as a form of probabilistic distributions, aka beliefs about how, for example, the first equation shows that how the x dot, the velocity of the world, is dependent upon where the world is, x, which is denoted as x, and also the nu and theta. And you see that we have normal distributions here because these random fluctuations are zero mean with some precision matrix pi x and pi y. So basically, mathematically speaking, these probabilities will become normal with the expected value f and g, and the precision matrices will be directly inherited from random fluctuations. Now, digging a little deeper about the generative model and its joint likelihood. So the first two equations are the ones that we've already discussed. And we said that if omega x and omega y, we're assuming them to be smooth Gaussian processes, some unknown functions, basically. So the implied marginal distribution at time t, please pay attention when I say time t, because I'm going to move beyond time t in a few seconds, okay? So at any given time t, you can encode the rate of change in x, dx over dt, as the normal distribution that I described earlier, and also, again, observation is defined as a normal distribution. All of this normal distribution is the way we're defining it in both of these as normal distribution is because we are assuming the smooth Gaussian process to be the right mathematical approach in modeling omega x and omega y. Again, we have the precision matrices pi x and pi y, and it's important to note that we are mathematically modeling pi x and pi y with some hyperparameter lambda. Basically, in the future, when I talk about uncertainty estimation, I'm talking about estimating these lambdas. In other words, what's the generative model's uncertainty about the dynamics of the world? Also, what is the generative model's uncertainty about the observations, the noise in the observation that it's receiving? So two types of uncertainties are defined by these lambdas. Now, let's say we want to go beyond time t. In other words, can we endow our generative model with the ability to be able to look at a little before time t, but also a little into the future after time t? In other words, a trajectory that goes through time t. So it's endowing the model with a sort of sense of memory and also some predictability about the future. And that's the world of generalized coordinates motion. So the temporal dependencies are recovered via generalized coordinates. So previously in the previous equation, you saw we had dx over dt, but why not going to higher temporal derivatives? Why not go to not just the velocity dx over dt, but also go to, let's say, the rate of change in velocity, that is acceleration? Why not higher? Rate of change in acceleration, which is jerk, and so on and so forth. The same story with the observations y. We can have y, the rate of change in y, the rate of change in the rate of change of y. So basically the two equations of the general model can be differentiated with respect to time consecutively. So by differentiating the generative model's two equations, all of a sudden you're dealing with these systems of differential equations where, for example, the left-hand side, you see that d2x over dt2, which is the time derivative of dx over dt, which we're denoting as x double dot, meaning that x dot was the time derivative of x. Now x double dot is the time derivative of that of the x dot, right? So in other words, that is the acceleration. So this equation, I don't want to get into the details, but if you do the derivatives, the time derivatives with respect to the generative model, this is what jumps out of it. The dots all refer to time derivatives. You can do the same with the y, with the sensation equation, with the observation model in the generative model. And one thing to note is that you notice that if you keep differentiating and go to higher generalized coordinates, you notice that the equality suddenly turns into an approximation. And this is basically because we are assuming that this Jacobian term over here is constant, meaning that the dynamics shouldn't change that much from time t to just a little after time t. So because of that, we are keeping this becomes an approximation, but it will keep things more simple. So we can define these long equations no matter how many generalized coordinates you have. We can just define it as one sort of notation as sort of one differential equation where x tilde, for example, here is just a vector of all of the generalized coordinates along the x-axis, which is x, x dot, x double dot, x triple dot, and y tilde is y, y dot, y double dot, y triple dot. And interestingly, again, because we had omega x and omega y as smooth Gaussian processes, again, the derivative of a Gaussian process is a Gaussian process. So in other words, this entire system of differential equations that are being described in one line like this, the same story with the right-hand side, this again is normal, actually. So again, you have the same Gaussian distribution behavior in these. The d variable is just a differentiation operator. Basically, it moves things forward in the generalized coordinates dimension. So that just something that allows us to describe all of these equations as one equation very easily. Now, variational free energy, let's just also describe that. So again, the goal is to do triple estimation in an online fashion a posteriori. The things that we want to estimate and learn are the x tilde, which are the hidden states, but the tilde means that not just the hidden state x, but also all of its temporal derivatives. In other words, the generative model will have a belief about where the world is, the velocity of the world, the acceleration of the world. It has to learn to estimate those as accurately as possible. If it can do that, that means the perception is close to what it should be. It means this entity, the brain, will not basically lose its mind, and it will persist through time in a harmony with its own environment beyond the Markov blanket. So that's crucial. Next one is theta, the model parameters. These are assumed to be not moving with time, sort of very, very, very infinitely slowly moving variables with time. The lambdas are the precision or hyperparameters that I discussed before, encoding the uncertainty. Now, For simplicity, I'm just going to put all of these three x tilde, theta, and lambda as in, just going to define it with one variable psi. So basically, the joint distribution along all of these can be defined as this. So here you have the model, the likelihood of x tilde and y tilde given the model parameters and hyperparameters times some prior over these thetas and lambdas. However, unfortunately, the goal is to minimize variational free energy because you want to be able to estimate the posterior probability. In other words, you want to be able to model human perception. The perception has to happen. That's how it happens. So the problem is that the posterior, the exact posterior, is intractable. So that is why we have to resort to some other approach to be able to estimate that unknown posterior. In other words, instead of an exact calculation of your posterior belief about the world, you need to have some tractable but approximation of the posterior belief about the world. So that approximation is defined as this Q distribution over psi, which has some mu, which is the expected value, and some covariance over psi. Again, follows a normal distribution. So this is going to be an approximation of the true exact posterior that is intractable. Of course, it can be tractable under some, in some limited situations, in some small examples, but in general, it's not tractable. So the goal is that, so we're going to be using using this Q to be able to approximate the posterior belief. If we can do that, perception has been accomplished. So digging a little deeper, VFE is it's a function of another function because it's a function of Q, which is also a probability distribution. That's why we call it a functional. By the way, that's why we say variational. When you're dealing with variational, it means you're dealing with functionals. You're doing optimization with respect to a function, not a variable. So VFE is a functional of, we have the Q there, and we have also the exact unknown posterior, remember. It is, I'm not going to be going into the details, but it is just an expectation over minus log joint distribution that we've seen before, plus the log of this surrogate posterior Q that we're using to estimate the unknown posterior. Now, ideally, what we want is we want a Q that minimizes this VFE. But the problem is that Q is this VFE is not usually provided in closed form. That's a big problem. It's basically this expectation is kind of a nasty expectation, statistically speaking. So the solution is that we can resort to Laplace approximation, meaning that we can basically estimate or approximate all of these distributions, the Q, the P, the joint, through quadratic approximation using Laplace approximation, meaning that we'll do the approximation all the way to the quadratic term, and then the remaining bits are just, we're going to leave them out. That's just going to be the approximation error. The interesting part is that the first term is free of psi, free of x, theta, and lambda. And here in the quadratic term, you have the curvature. So this will make so if you basically do the approximation for the joint and Q, and then put back these approximation into the definition of VFE, all of a sudden we will have a closed form description of VFE. And if we have that, then it's easy to do the optimization with respect to Q and make Q as close as possible to the posterior, hence making perception possible. So once we do that, putting the Laplace approximation estimation of the joint and Q into the definition of VFE, we get into this sort of formulation. Unfortunately, I don't have the time to go through all of that. You notice that this is an approximation because we're doing approximation here. So the key thing is here we have this this joint distribution as before. However, the second term the key thing is it is free of these expectations over psi, right? It's important because the optimization will be with respect to these mu's, and because of that, the calculating the derivatives will become much easier because we have to deal with this first term over here. For those of you who might be interested, this second term involves the anthropic terms and also the prior terms, the likelihood terms, and some constants. But they're not a function of these mu's. Interestingly, the posterior of the covariance of the posteriors, they don't need to be estimated. They are a direct analytical function of these expectation mu psi. So you don't need to infer them, you don't need to learn them, you can directly calculate them. So the whole idea is that through minimization of VFE, we are focusing on estimating and learning these mu's over psi. Again, psi consists of the fast-moving states x tilde, basically, in generalized coordinates, theta, which is the slowly moving variables, and also the lambdas that encode the uncertainty of the model over the data and the dynamics of the world. Now, basically what we want is the mu psi that would minimize VFE, right? Now, of course, Q can be of any family of the family of distributions, and that means the search for the right Q would be really, really difficult. And that is why we will use mean field approximation that assumes a certain independence amongst the key components of, in our formulation, meaning that Q can be factorized into 3 independent distributions: 1 over x tilde, 1 over theta, and 1 over lambda. And this would allow us to estimate each part of x tilde, theta, and lambda separately. This would introduce some error into modeling perception, but this will also come with a lot of simplicity in the calculation and finding an acceptable Q. Again, remember, the goal is not to really know what's happening in the world. It could be different from the actual unknown truth. The goal is to be able to find an understanding about the invisible worlds that is good enough for you to persist through time as a generative model, as the brain, to persist through time and continue with your life. But you will never know the truth. That's really important to mention. Now, connecting all of this to predictive coding, which is a generative model for modeling human perception. We have used this predictive coding to model human perception, by the way. Now, predictive coding, it's a powerful framework to describe how the cortex accumulates evidence from noisy stimuli. It is an application of free energy principle, the same way that active inference is also an application of the free energy principle. But here, there is no concept of action. It's completely passive sense-making of the world. So predictive coding, or PC, focuses on how the brain can perform probabilistic inference about the most likely hidden cause that has caused the sensory signal. Basically, the probability of X, hidden state in the world, given Y. The same thing that we talked about in the Bayesian brain hypothesis. PC assumes that the brain has a generative model of the world through which it constantly infers the hidden causes, and also learns the parameters of its own generative model, also estimates its uncertainty about the world and the data. Finally, model inversion. Whenever you hear about model inversion, it means we want to use variational approaches, variational calculus, to be able to estimate the posterior, the unknown posterior. All of this happens by minimizing variational free energy. Important thing, when you minimize variational free energy, you're doing 2 things. Number 1, you are reducing the distance between your surrogate posterior Q with the unknown posterior distribution, which is P, or I think I denoted it pi. But my point is, your Q would move more and more towards the unknown posterior posterior probability. That's one thing. The other thing is the actual value of VFE becomes a proxy for or an approximation for the intractable model evidence. Model evidence is the key quantity that we can use to compare our generative models with one another. And because it's not tractable, we use the actual value of VFE as a proxy to be able to compare one generative model versus the other generative model in their sense making of the world. Basically, one model perceived the world better than the other model. So this is the sort of pictorial depiction of predictive coding. You have hierarchies here, and each hierarchy, interestingly, has this sort of generative model sort of formulation that I've described before. Everything is Hebbian, meaning that the same generative model that I described is embedded at each level of the hierarchy. So each layer wants to make sense of the layer below. By below, I mean more shallow layer. And the deeper layer is basically doing variational free energy minimization to be able to do that. And then a collection of all of these local VFE minimization becomes a degenerative model that basically you can think about the total VFE as a sum of these individual local VFEs. So again, here we have what happens is we have top-down predictions, meaning that deeper layers would make predictions about what's happening in the more shallow layers, all the way to the first layer that would make prediction about the actual, because remember, the first layer has no layer before that. That's the skull, basically. The next thing is skull and the world. So it cannot predict anything about any layer below itself because there is no such layer, but it can predict the actual sensations. That's why you notice that we have Y here for layer 1 being predicted by layer 1. However, for the layers in between, each layer is predicting some quantity new that resides in the layer below. These are the causes, these news that I talked about. I'm going to talk about them a little more in more detail. So top-down predictions are made all the way to the Markov blanket, right? And then you've predicted the sensation collectively as a hierarchy, and then the actual sensation comes in. So you calculate the difference between the two. That's the prediction error, right? And then this prediction error is calculated, and then there is bottom-up information trajectory where these errors, prediction errors, are sent up from the superficial layers all the way deeper into the hierarchy. And then the deeper layers will try to tune themselves through triple estimation that I'm going to be talking about so that the next predictions will be more and more accurate. One keen thing here is that, just to be a little pedantic here, the bottom-up messages are not just prediction error, they're actually precision-weighted prediction errors. That's really important. This precision is the thing that will encode attention mechanism, by the way. Also, model inversion happens and posterior estimations are adjusted, meaning that the Qs, the surrogate posterior, are adjusted to be closer and better approximation to the unknown posterior belief. And basically that allows for perception to happen. So one-layer predictive coding model. I'm just going to talk about the one-layer structure here really quickly. The big picture, I'm going to be talking about D, E, and M steps during this optimization, and also the triple estimation loop. So one-layer predictive coding. Again, the same equation that we've seen before. So basically, some error terms are calculated. We have the prediction error over the sensations, Y. We have the prediction errors about the dynamics. Here, you can think about d mu x as, let's say, the velocity, for example, to make it simple. So the x's and thetas are being used to make predictions about the estimation about velocity. Also, we have two error terms about the thetas, mu theta and mu lambda, which is basically the distance between the expected posterior about theta and the prior expectation that we have. In other words, by minimizing these errors, we are regularizing the estimations over mu theta and mu lambda by using the priors that we have. So priors are the regularizers in the realm of Bayesian statistics. But then we calculate VFE, variational free energy, and then model inversion happens when we are updating all of the expected values, posterior expected values over thetas, lambdas, and x's. We can go over this during the Q&A if you want to dig deeper here, but this is just some sort of you can think about it as a gradient typical gradient descent approach for minimizing an objective function, basically. So here you have the gradients which is of the free energy with respect to the quantity, the mu's, the modes of interest. You will update your expected posterior. These expectations are the expectation of your surrogate Q. Remember, we don't have the true posterior. And then you might wonder, okay, these Q's are Gaussian. What about their precision or covariance matrix, for example? Do we not need to also estimate or calculate the gradient of VFE, free energy, with respect to these covariances? The answer is no. As I said, these covariances are analytical functions of these modes. So if you estimate these modes, the next step is to directly calculate these covariances. And then you move on to the next observation and next observation. It's a loop in an online fashion that I described. So I'm going to define true perception as an online triple estimation. So the first key of the triple estimation is inference of hidden states. We call it the D step, the deconvolution step. Those of you who are familiar with, I think, stochastic DCM, if I'm not mistaken, is using DEM, dynamic expectation maximization, under the hood. The D, E, and M steps are basically are inspired by the DEM algorithm. So we have the step here, which means that I'm going to do state inference. I'm going to be inferring the X tilde about the world through intralayer activation. So you remember we talked about the how we use the flow of the state dynamics to make predictions about the higher temporal derivative of X. So that's why I'm calling it intralayer. But interlayer communication is all about inferring these hidden causes, these news. That's why I'm calling it interlayer communication. So during the D step, these two will have to be inferred. Next, we have parameter learning. We call it the E step. Parameters are denoted as theta. These can be looked at as, let's say, the synaptic weights in the brain, for example. And then we have uncertainty estimation, the M step, where we have precision matrices over the hidden states X and also over the observations. Again, you notice we have tilde over all these variables. It's just basically saying that we are in the world of generalized coordinates. So anything that has a tilde over it, it's a vector of that thing and all of its higher temporal derivatives, right? So just a quick note, through uncertainty estimation, we are modeling attention, not in the sense that you've seen maybe in the world of machine learning in transformers. This is a different kind of attention that measures how much I'm going to be attending to my prior belief versus to the data that I'm receiving, the evidence I'm accumulating, let's say, from the world. Now, if it's defective, it will cause some form of synaptopathy and, for example, hallucination or some sort of issue in the brain. Now, I'm going to be talking about the separation of temporal scales. Particularly, I'm going to be talking about the ODEM and SODEM algorithms that we have developed. Online dynamic expectation maximization and separated online dynamic expectation maximization. So the generative process in the world, it has different levels of dynamics, slowly evolving, faster dynamics, so basically the slowly evolving dynamics provide the context about the world. For example, it's now daytime and it will move slowly towards nighttime, right? But upon that slowly moving dynamic, we have faster dynamics that are unfolding. They are the content that are unfolding over the slowly moving context. So a true free energy minimizing generative model aims to persist through time, right? By minimizing free energy. It aims to reach a generalized synchrony with its own, with the invisible world, with the generative process. So it needs to model the interplay between different levels of this temporal hierarchy in the world. It has to have that math embedded in it as some sort of prior, let's say. So similarly, a predictive coding network can model such separation through, let's say, adding more layers, adding depth, where deeper layers provide context for more shallow layers upon which they can unfold through faster dynamics, or through parametric separation of temporal scales, that I'm going to be talking about. Well, I've basically mentioned them already, the x, theta, and lambdas. We will update them at different paces to basically endow the model with the prior that we have a separation of temporal scales between different variables in our formulation. So this is the online dynamic expectation maximization pseudocode that we've developed. I'm just going to be, I'll go over it very, very fast because unfortunately, I'm running out of time, but we can get back to this later on. But the important thing is the most outer loop over here is over the observations, right? So for every observation, the following will happen. First, we have the D step that does state inference. So we have some iterations in this for loop over the D step, over which the estimations of the hidden states will be updated by calculating the free energy and calculating the gradient and so on, right? So for one observation, we have many D-step iterations. And then we will accumulate the gradients with respect to the lambdas and the thetas, because we are endowing the model with this kind of scheduling that is basically saying that we are not going to update mu lambdas and mu thetas. We are basically, we're not going to update them as fast as mu x's, because we believe that these two quantities need to be updated at a much slower pace than the state dynamics x's, right? So we are creating that separation of temporal scales by this particular scheduling. So we are just accumulating the gradients with respect to these two variables, but we're not updating them yet. So you see that here in this if statement, we have this parameter learning, which is updating mu theta, and also uncertainty estimation, which is updating mu lambdas every now and then. So every time this this iteration variable is set, let's say every 128 or every 256 observations, we will apply these accumulated gradients, right? So they will be changing in a much slower fashion. And then we will recalculate we will calculate the posterior covariance. As I said, these are analytical functions of the mode. And then we will calculate VFE, and then we will accumulate VFE in a variable called free action. So for every observation, we will calculate VFE, and we will add it and accumulate it. And after the entire triple estimation, through our entire observations, we will end up with one value for free action that will be used to compare different general models with each other through triple estimation. So the accumulated variational free energy is the metric for evaluation in an online setting. The next bit is separated ODEM. The only difference here is, again, we have state inference, we have gradient accumulation, but the E step and M step are happening at two separate time scales, meaning that the uncertainty estimations for mu lambdas are happening in a much more frequent manner than that for the thetas, right? In other words, we're saying that let's say, for example, the noise in the data from the perspective of the generative model, the noise is changing much faster than the parameters that are assumed to be infinitely slowly moving, but it's still not as fast as the state dynamics, right? That's why we're not updating the lambdas with every observation, but every few observations. But again, remember, we are doing gradient accumulation. For those of you who might be interested, this is accumulation through exponential smoothing, right? Again, posterior covariance and so on. Now, I'm just going to show you some experiment results between these two algorithms, ODEM and separated ODEM. So this is X star here, the generative process. We have designed this as a solution of a Lotka-Volterra process. This is displaying the role of the invisible world, basically, X star. We add some smooth noise to it, and we end up with the observations. But the way we've done it, we have deliberately, as time goes by, we have increased the precision of the noise over data, right? In other words, we're saying that the precision of the noise it's changing. It's not changing as fast as the dynamics of the dynamics of Lotka-Volterra process, but still moving reasonably, but still changing slowly but smoothly. So in other words, I'm saying that there is a separation of temporal scale already. The reason we've done that is because we want to pit ODEM and SODEM against each other for this kind of generative model and this kind of sensation, and see whether the model that has that separation of scales would do better in a world that actually has the separation of scales between the parameters and the noise precision. Again, here the parameters are fixed because we have just fixed the parameters of this generative process, alpha, beta, and the other two parameters in order to before solving them. So the parameters are fixed. The bit that is changing is the fast-moving dynamics, hence the trajectories. Also, the more slowly moving noise in the data that you have this slowly increasing the precision of the noise. So we just use just for this presentation, we just use 3 different generative models. Basically, a trigonometric generative model, which has the state, basically the flow of the state dynamics is modeled as a trigonometric function with an A vector that is a 2×1 vector in this case, y2, because here we're dealing with a 2-dimensional generative process and 2-dimensional observations. And the G function is linear. Right? It doesn't do any transformation over x's. Then we have a pullback attractor, typical pullback attractor with the center, with our center here. And also, again, here A is a 2×2 matrix, and the center is a vector of size 2. This means that the generative model believes that there is a point where the world is being attracted to. That's the center of it. And the last one is actually a Lotka-Volterra process, but this time we're using it as the generative model. Again, the generative process is the solution to the Lotka-Volterra process that we've seen before. Remember that here we're going to do triple estimation. So the parameters, x's, everything will be estimated. Interestingly, here you see that along the 3 generative models, ODEM versus SODEM. SODEM is the one that has a separation between the lambdas and thetas. If you look at free action FA, comparing the two, again, free action is the accumulation of variational free energy along the entire triple estimation process. You notice that SODEM is always doing better than ODEM for this particular world with the inherent separation of temporal scale. Just for reference, I've also put the MSE of the actual inferred states and the true states of the Lotka-Volterra process, as to also show you the accuracy of these 3 different generative models. Interestingly, for SODEM, it's the MSE is very, very slightly better, but let's just say they're almost equivalent. Interestingly, it's as if during SODEM the accuracy is basically has been preserved while lowering the complexity of the model. In other words, and that's how the free action is always consistently lower compared to ODEM. So let's just focus on the trigonometric generative model, because that was the winner out of all of them. So again, here state dynamics is a function of is a sinusoidal function with a vector A. Vector A holds the parameters of the generative model. X is the hidden state variable, 2-dimensional. Observation model is identity. And here, for the SODEM algorithm, we are keeping the iterations of the D step for state inference as 8, meaning that for every observation, 8 iterations for the D step will happen to make a better and better estimation about the hidden states. Also, the interval for the E step for parameter learning is chosen as 128, meaning every 128 observations, I will apply the accumulated gradients with respect to theta. And also the interval for the lambdas, in this case, is chosen as 4, meaning that every 4 observations, I'm gonna recalibrate my precision estimation. So again, X star is on the top, the invisible generative process. Y is the observations that the generative model, the one-layer predictive coding, will receive. And given that Y, it has to infer the X star, the generative process. And it has done interestingly well. It is filtering out all the noise. You notice that in the observations, we have negative values even on the vertical axis after having added the noise, but it has managed to bring most of them toward the positive side, which makes sense for the Lotka-Volterra process. Also, you can look at the actual generated observations, predicted observations, along the first axis y0 and the second axis y1 of the observations. So on the left-hand side, you see the first dimension of our observation vector y0. The green curve is the true observation, and the purple curve is the predicted observation. You remember that I said predictive coding is making predictions, top-down predictions about the world. The error is calculated, and precision-weighted prediction errors are sent bottom-up, right? So these are the actual predicted sensations or observations. So the pink, or let's say purple predictions are basically the predicted sensations. You notice that the predictions are sort of resisting against the fluctuations in the observations. So they're not exactly following the noise, which is a good thing, especially for the second dimension of y. You notice that here, especially, it is moving it is basically predicting along the trend of sensations, not following exactly the noise, which is a good thing. The one thing that we were surprised about was that the parameters of this generative model, yes, we are doing slow updates. Yes, the prior knowledge is that the theta should move very, very slowly. But one thing that was surprising to us is that the initial values that we've picked, there are very, very small updates here. I mean, every 128 observations, granted, but the value of update to the accumulated gradients is pretty, pretty low. So that's a little bit strange for us. Also, these are the uncertainty estimations over the y, the observations, and the x's. You notice that the precision, these encode precision. So you notice that the precision is going down and down over the observations, which is expected because the noise is increasing. Also, on the right-hand side, this is the precision over the states. That it seems to be going to converge to some values. Now, from one-layer predictive coding to two-layer predictive coding model. Again, my apologies. This is getting too long, but there are just too many slides. I have to go over them so that we can have a discussion about these. So the second you add the second layer, things change. All of a sudden, you have these new variables that are called causes, as I referred to them before. These are used to make the layers talk to each other. So in other words, layer 1 is the most shallow layer. Layer 2 is slightly deeper into the hierarchy. But you notice that layer 2, through the observation model, makes predictions not about the sensations. Why? Because it is nowhere near the Markov blanket to be able to make any predictions about the sensations. But it makes predictions about this variable called nu, that we call as cause, that lives in layer 1. And it makes predictions through its observation model. And through this prediction, all of a sudden, the two layers are talking. So as an example, you have a sort of rescaled version of Lorentz attractor, typical chaotic behavior attractor that everybody uses in dynamical systems. Again, in layer 1, the flow is governed by this Lorentz attractor. You notice that two of the variables of the coefficients we have named them as nu. These are to be predicted by the Lorentz attractor in the deeper layer, in layer 2. In other words, in our generative model, we will code this up or do the math such that, for example, in layer 2, the second and third dimensions of the hidden states, x, plus some random fluctuation, is going to be the prediction for the new one in layer 1, right? And you notice that in layer 1, we are using the second and third dimension of x1 and the random fluctuation to make predictions about not new zero. There is no new zero. There is only sensation because it's right next to the Markov blanket. Now we get to the questions and concerns that I'm hoping to get your guidance about. First, about our experiment setup, we have a big set of experiment parameter grid that we have to go over. So we have picked 3 generative processes. One is a Lotka-Volterra, the other is a Lorentz attractor system, and the other one is a 2-dimensional pullback attractor. It's a rotational pullback attractor, meaning that if you look at the eigenvalues of the state dynamics matrix, you notice that the real part of these eigenvalues is 0, so you only end up with the imaginary part. So you have this sort of cyclic behavior, but it will converge to a particular point. That's why it's still a pullback attractor. So the generative process is the solution to these systems of differential equations. The generative models, again, we put Lotka-Volterra, Lorentz, and a pullback attractor. The number of nx is the number of iterations per d step, per observation, meaning that we will do 8, 16, or 32 iterations over in the d step for a better estimation of the hidden states. Kappa is, well, I didn't go through this in the interest of time, but this basically controls during the d step how much am I gonna pay attention to the gradients of free energy with respect to the hidden state, let's say x, for example, versus how much I'm gonna pay attention to my estimation about not x, but x dot. In other words, this is how we are weighting between the gradient with respect to, let's say, position versus our estimation about velocity of the world, right? So if kappa is high, it means by estimation about the velocity of the world is dwarfed compared to the actual gradient with respect to the position of the world. But the other way around, that means I'm giving a lot of weight to my estimation to the velocity of the world and much lower weight to the gradient with respect to the position of the world, right? Higher, lower kappa means that I'm going to be more adventurous. So I'm going to be, exploring more and more because I'm basically giving more weight towards higher temporal derivatives. So interval lambda controls how frequently am I going to do the m step for precision estimation. Interval theta, the same, but this one for theta. These ones control the separation of temporal scales, right? So every 200, for example, this means every 128 observations, I'm going to do 1 update of the parameters, 1 e step. But this one here, 4, means every 4 observations, I'm going to apply the accumulated gradient to my estimation about the my uncertainty about, let's say, the world or the sensations. Here, this is interesting. This is how we are, changing the variance or the precision of the noise as time goes by, right? To actually make the actual sensations with a separation of temporal scales between the noise and the actual hidden states underneath, right? So, for example, 0.22 means that let's say the variance or the standard deviation of the noise would go from 0.2 all the way to 2, meaning that let's say the variance for simplicity will increase from 0.2 to 2, right? So we'll have less and less, fluctuations as time goes by. So the precision is basically going down. Beta lambda and beta theta, they're controlling the exponential smoothing during gradient accumulation, meaning that because it's online, these control, as I'm, let's say, collecting gradient with respect to, let's say, lambdas, how much am I going to pay attention to gradient at time t right now versus the accumulated gradients in the past, right? Whereas at 0.5 means they will be weighted equally. 0.1 means mostly I'm going to pay attention to gradients near to time t, and I'm going to mostly ignore what happened in the past. The last 2 bits these are related to the priors that we define over the thetas and over the lambdas. So again, these are Gaussian priors. So we define a grid of expected value and variances for these Gaussian priors for theta and for precisions, the lambdas. So in total, we would have nearly 8,000 combinations of experiment parameters, and we have 72 prior combinations that we have to tune during triple estimation. So what happens is, for a given experiment combination out of those 8,000, we will do first prior tuning with only 10% of the observations, meaning that in an online fashion, the observations are fed in, VFE is calculated, accumulated through free action. For every prior, we end up with a free action after having observed 10% of the data and having done triple estimation. We will pick the prior with the lowest free action, and that will be used for the entire triple estimation for all of the observations. So after we pick the best prior, we'll run the online triple estimation through either ODEM or SODEM with the optimal prior. We save the total free action for the current combination and the best prior that was used for it. Right? That's what will be saved at the end of the experiments, and the best model is the one with the lowest free action. So first questions. By the way, I've already asked these questions at the previous UCL meeting, but there was not enough time, and I'm using this opportunity to reiterate these questions. Hopefully, we can shed more light on that. So, for example, the question is, what other options for F and G are available out there? So, how could we determine the functional form of these two? That's basically one question I have. Also, in general, when we use this G function in a given layer to make predictions about the causes at layer n, the more shallow part, what should be the functional form of this G function? Do we have a principled way of doing it? And also, given a particular form, what is the logic in determining what variables in this state dynamics equation, for example, should be, let's say, the causes, which coefficients should be the parameters, for example, what determines that separation, mathematically speaking? So in the case of high dimensional data, how do we do this dimensionality reduction as we go deeper and deeper? So is it possible to gradually reduce the dimensionality layer by layer in a manner similar to deep learning, but not exactly like that? So in deep learning, we have this gradual, reduction in dimensionality, but deep learning is different inherently from what we're doing here. It is deep, but the way the neurons talk to each other is very different. So how should we do that dimensionality reduction? The other one is, how else can we impose this separation of temporal scales in a more neuromimetic fashion that is inspired by how we know how we think the brain does it, actually? For example, the number of updates in the D, E, and M steps. Is there a principal way of determining that? Or do we have to just go, full brutal mode as a grid search, for example? What about the number of generalized coordinates? This one is really, really tricky, because we've observed that as you move to higher generalized coordinates, you will be dealing with higher and higher instability in the values that you get, because the DT value when you're estimating, let's say, y dot, y double dot, y triple dot, there's this constant division by a very small time, right? Let's say the sampling interval. And the more you do this division to go to higher generalized coordinates, the value of that division becomes more and more larger and larger, and it will explode eventually. So how do we deal with that? Also, about model comparison, where two models are equipped with different numbers of generalized coordinates. My question is it fair to do this comparison? Because one model is also using higher, not just the observation vector, but also higher temporal derivatives or estimations of those derivatives of the observation, y dot, double dot, triple dot. I know that these are not basically really new data, new observations, but they are being calculated by this model. So is it still fair to compare the free action of these two models, where the other one, let's say, has only 2 generalized coordinates versus the other one having 4, for example? So the expectation and precision values for prior distributions over x, nu, and theta. Is there a good way, a principal way of determining these priors or not? And basically, if you have any thoughts about like any other potential considerations that we might have skipped over, please let us know. So the order in optimization is the other question I have. So in the interest of how the brain works, do we know whether the optimization is happening layer by layer, like minimize VFE in layer 1 and then minimize VFE in layer 2 and go on? Or is it happening entirely together simultaneously? This matters because this will affect how we're going to code. I mean, we have code, how we're going to code this hierarchical structure. So as an example of what I was talking about as to how we choose these Fs and Gs, this is an example from a particular literature where we have a two-layer stacked up Lorentz attractor systems with identity G functions, observation models. So here, layer 2 is the deeper layer, which makes predictions about the causes in layer 1, and that's how these two are talking. So these are, for your reference, Lorentz attractor's function looks like this on the bottom, just for your reference. So in layer 1, the rho and beta parameters are selected as causes. And the question is, why these two? Right. Also in layer 2, x2 and x3, as you note here, are being used in the observation model to make predictions about these causes in layer 1. So again, why x2 and x3? For the coefficients, we have used these particular three values. Again, is there a reason why these, for example, do we insist these Lorentz attractors to behave chaotically? Or are we interested in, let's say, quasi-periodic behavior or not? Like, what's the logic behind choosing these values, for example? Also, why, like in this particular literature, the original Lorentz attractor had been slightly modified by introducing these two coefficients over here. As you see that in the original Lorentz attractor, we don't have these two. So we're just curious if there's a reason that you could think of as to why these modifications are generally applied to such models. Again, in another literature that I couldn't find, I really tried, but I couldn't find it. The G function this time is different, meaning that in the second layer, only the third hidden state was used, and then -4, and that was the prediction about the causes in layer 1. Again, we cannot figure out why these particular functional forms are being used in the observation models on a given layer for making predictions about the causes in the layer below. So if there is a principal way of thinking about this assignment, we would appreciate it if you could guide us. And the final question, how to pick priors in hierarchical models without resulting in a Lindley's paradox. So that is, just briefly, two vague priors that are like really, really flat, let's say, or really, really wide, can result in arbitrarily low model evidence and especially higher dimensional models. So is there a way to avoid this? So if they're too precise, that might, we might fall from the other side. Like it could result in a very bad VFE. In other words, there would be too much weighting towards the priors, and then we might not be able to actually, even do proper evidence accumulation and give the value to the data, to the observation that the data is due. And lastly, is it possible to estimate the uncertainty in an online manner without ever needing to bin the data? Meaning that if I'm gonna instead of just doing it like let's say accumulating, let's say 32 observations and then estimate the precisions, especially those matrices, is it okay that, or is it possible to do it purely in an online fashion the way we're doing it here, or are we introducing a lot of error here? And finally, acknowledgement goes to the Marie Curie Grant Fellowship and that I'm under. Also, huge acknowledgement and appreciation towards our supervisors and mentors, and also our colleagues at Monash, UCL, MIT. And thank you so much. And my apologies that it took a long time, but it was just too much that I had to cover. Thank you very much.
No worries. Thank you so much, Mehran, for the presentation. So now we move to the Q&A. So if there are like any questions, please raise your hand. Yeah, I don't know how much time do we have, Carl. If yeah, we can have like a brief Q&A because we have like 20 minutes left only. Just regarding the last thing you were saying about binning the data, like, isn't it? How else can you measure uncertainty if you don't have like a? Because it's a second order statistic, right? So you need like a bunch of data and from there like estimated the variance in there or something. So like feels like purely online. Yeah, how would you do that like purely online without like keeping track of some sort of history, right?
Yeah, so through that exponential smoothing, as we're accumulating the gradients, that's how we are sort of keeping a record of the history of it. But again, that would introduce some error into the equation. So
yeah,
we wonder if we can do, like, if it's okay to do it this way. We want to do it online, basically. That's
and just I'm curious, like regarding the Lotka-Volterra results you were showing, did you see any difference in terms of like uncertainty estimation between the two, like the SODM, I think it was called, and the, between the two models? Like, was there like a significant difference in that sense?
Yeah. Well, the problem is that the experiments are currently running. We have like around 8,000 experiments.
Oh, okay.
And we haven't got the optimal results. So the values that you saw in the table of results are they're not even the best values, the best reactions that those particular generative models could achieve, basically. So I just put in there as some preliminary results to show a comparison between different generative models. But no, we haven't had the chance to do that yet.
Okay. I see. Yeah, well, there's a question there, so I'm just gonna move there. I had like another one, but let's leave it there. Thank you, no worries. So yeah, Andres, you have your hand raised.
Yes, briefly. Thank you for a great talk. I was very interested in the notion of the causes, and it made me think about Charles Sanders Peirce's three kinds of signs, the iconic, indexical, and arbitrary. And so I think of the two hemispheres. There could be one that's working with the first layer, and then the second layer could be, so maybe it's iconic information in terms of positioning and things like that. And then the second layer could be, popping in every 120 on a different time scale, 128 or so. And it's tracking, let's say, causes or indexes or whatever. And then those two could be linked by arbitrary symbols. So there could be a tiny CPU, maybe in the thalamus, that's kind of saying, okay, here's, I want to set this parameter, reset it or whatever. But you have these huge, big, giant brains, and then they're steered cybernetically by a tiny CPU.
I see.
And just in terms of, just to finish, in terms of body of data, I'm interested in studying triangle geometry as a corpus. There's an encyclopedia of triangle centers, like, special points for an arbitrary triangle. You can build like 60,000 different points. It keeps growing, this encyclopedia. But it's like a corpus for a language. So if you're looking for, I'm looking like for a paradigmatic language that would explain, if I can interact with a triangle, I could interact with a dolphin, I could interact with a cloud, So it gives all the possible notions, so the actions, like you take a circle and you shrink it, or you put a circle and you expand it. What are I think there's a vocabulary of actions, and there's a vocabulary of concepts, which would be like the centers of the circles, let's say, or the different points you can construct. So one would be like more, I think the actions, in a certain sense, they're more like the unconscious, that, and they're dynamic, let's say. But the other ones are this static language. And then you have like different ways of constructing the same points. So you get like a language of equivalences, let's say. So like so these three languages, I'm just hoping to study that. But so that would be a very different type of thing to study than what you're doing, because even your work, it seems like those causes are super abstract. Like if a window rattles, it could be the wind, it could be a mouse, but it could be a ghost, or it could be nothing at all. And so the mind is not picturing a mouse when it connects those things. It's not necessarily like, it's very interesting, like where these causes, but what they're doing is that they're indicating what that Markov blanket of causes is. You know, that every point in that Markov blanket, I suppose, is a cause, and there's this causal blanket, and it's absolutely abstract, but it's just kind of like coherently, consistently figuring itself out based on what I think is another, you know, blanket of input information. So there's this, I don't know, but the way you talked about it, there's divorce between these. I think of it like as a passive inference and active inference, and there's a chasm. So those are my comments. Thank you.
I see. Thank you.
Cool. I think, yeah, maybe if we can move to you, Carl, because there are only 15 minutes left. So
Yes, of course.
Yeah.
Yeah, and I don't know that 15 minutes is going to do it for us, but at least now we have a documentary record of the questions. So, Mehran, I think the best thing to do would be do what we can today, but bring back this slide deck to a methods meeting, the first methods meeting you can do when Peter gets back from Brisbane. And then we can drill down on the many questions. I think at the moment, just in terms of what you're doing, the key observations that I'd reflect back upon you, I am worried that you're doing many thousands of simulations. That should not be necessary. You just need to do one simulation and then show the relative benefits of the different temporal schedulings of the D, E, and M steps under some carefully chosen fluctuation in the precision. The reason that I'm suggesting you don't do all of these line searches is that that kind of line search is just a form of Bayesian model comparison. You don't need to do that. You can do that using Bayesian model reduction once you've accepted that you can always associate a given model, or if you can associate a given model with a particular set of priors, then searching for the right priors just is searching for the right model. So this is a Bayesian model selection or structure learning problem, which is not what you are writing about. The questions at the end were all about how do I find the right structure for some given data. That's a Bayesian model comparison or structure learning problem. And you framed it in many different ways. How many orders of motion? You know, what's the functional form of the F's and the G's? Why was this particular variable chosen to link the levels? All of these questions, at the end of the day, are just what is the functional form of my generative model? Now, your application here is not to solve the structure learning problem. It's to solve or to demonstrate a series of solutions under a given model that will surface a separation of temporal scales among three different kinds of unknowns under the model. So you generate your data under a known functional form, and you know the functional form, and that is the functional form you use to demonstrate the relative performance of the different DEM schemes. So what I'm saying is don't waste your time doing thousands of simulations, because that's not going to interest anybody. You just need to simulate the data once, and then apply 1, 2, or 3 different inversion schemes to assess which is best, and having established which is best by just comparing the variational, the accumulated variation free energy among the 3 schemes in the way exactly that you have, you then drill down on the particular posterior densities over all 3 sets. So the latent states, you can show, as you did, the results in output space in terms of the posterior predicted density, but also crucially the posterior beliefs about lambda and theta plotted with the true values. When I say true, I mean the values that you use to generate the data. if you do that, then the key question now is the design of the generative process that really demonstrates the utility of having a separate E and M step for the parameters and the precision parameters respectively. And that depends upon the underlying temporal scheduling of the changes in the generative process. So I was noting that you got this sort of mono-exponential decrease in the precision parameters, which could reflect one of two things, and you need to be able to disambiguate. So first of all, it could be that you've just got your it's not kappa in this instance, but certainly the forgetting parameters appropriate or applied to the updating of in the M step. They could be too low here, and what we're seeing here is you get the same kind of results had you not changed the actual signal to noise ratio or the precision. So do you get this kind of convergence in the absence of any changes in the generative process lambda?
I haven't tried that yet.
Okay, that's the first thing to try then. So what you need to be able to do is to generate one set of data in a way that enables you to show that if you don't do this careful scheduling of the variational steps, or indeed, yes, if you don't do it in the right kind of way that is aligned with the separation of timescales over which these different kinds of unknowns can change, then you're not making your point. So what you have to do is to compare a situation where there is a change in the you first of all have to find a setup where there's a clear change in the lambda that can be detected.
My apologies. I think I misunderstood your earlier question. So I think I've done what you're talking about. So yeah, so I have some observations. Let's see where the noise precision is increasing smoothly and slowly as time goes by. And I've tried the two scheduling where one has that kind of separation of scales between parameters and lambdas and x's, and the other one doesn't have. And in the one that doesn't have, the lambdas are moving very, very slowly, nearly flat. So there is no such reduction happening. But with the one that does is what we're seeing here.
Right. What I had in mind is a stepwise change that has a functional form of a boxcar, so that there is a period of relatively noiseless and then a burst of relatively noisy data and then a return to high precision data. And then you should be able to show that your model can track this transient period of increased but sustained noise through the posterior estimates of the lambdas. So what I'd like to see is, first of all, these curves, but with the confidence intervals. And then I'd like to see the actual lambda that you use to generate the data. And what I'm looking for is the actual data being within the confidence intervals with some non-trivial form. I have to say that these smooth declines would be regarded by many as trivial, because it could be the case that lambda is exactly flat and the scheme is just slowly converging on the map estimate, on the most likely estimate. And the reader won't know looking at this, but if you put some structure where the noise goes up and down again, then it will be immediately obvious that you've been able to identify this at an appropriate time scale by comparing what you see in terms of the actual lambda in relation to the confidence intervals. And you just need to do this once. You don't need to sort of do it again and again and again and again. And you certainly don't need to, at this stage, do line searches over different priors until you get the best results. That's a problem of model comparison. And it's a really important problem, and we can turn to that in terms of Bayesian model reduction and various approaches and answer all your questions after you've done the first job, which is just to motivate an online DEM scheme or generalized filtering scheme, paying careful attention to the scheduling of what's going on. So that's what I would like to see in the first instance. Can I just go back to your pseudo code algorithmic description? Oh, actually, while we're here, let's just no, let's just stick with this, and then we can go through the sort of slides in detail at a methods meeting. Yeah, I think it might be visually or not visually, but sort of algorithmically clearer if you put your accumulation of the gradients within the loops over which you're doing the accumulation. So, for example, here your capital lambda sub ACC seems to be accumulating gradients as they are evaluated within the 4i sub x loop.
No, they're out. They're out of that loop. So
can you explain that to me? Because
sure.
For each I, and that's right, yeah, excellent. You've got a gradient. Yep.
Yes.
And how are you accumulating that gradient? You're accumulating it in the J, yeah?
So I'm accumulating it here for every y sub I. Here we have I sub x, so like these iterations will happen for that observation, this for loop over here. But after we have found the best mu x, for example, only then we will recalculate VFE with the best values found for the current observation y sub I, and for that observation y sub I, we will accumulate these gradients.
I see. So you're actually going through each batch.
I mean, technically like there are no batches here, right? So we're just doing it on the fly for every observation.
No, I don't understand that. So the I sub x 1 to nx, that's the entire entire time series, is it?
No.
No.
The entire time series is the most outer loop, y sub I.
Yeah. So how many data points have you got? Is it n sub x data points or?
No, it's capital Y.
Capital Y. So for the first time step, I'm going to now update my instantaneous expectation about the hidden states.
Nx number of times. So that's the iterations of the D step, basically.
Okay. Okay, sorry, that's thrown me. Okay, because online Bayesian filtering doesn't do that usually. I didn't realize that. I thought you were doing little batches and then intermittently updating.
No, so basically, as far as I understand, when we talk about gradient accumulation, we will calculate the gradient with respect to a given observation y sub I, and then we accumulate that gradient. However, before actually accumulating this gradient at these two steps, I'm just doing, let's say, for example, 32 iterations of D step to make better and better mu x's. And then, with those best ones found in an online setting, I can again recalculate this gradient, or basically reevaluate VFE in the first place with these best mu x's found, and then accumulate the gradients, and then apply them at different time scales depending on which one of these if statements are met. For example, every 4 observations for lambdas and every, let's say, 256 observations for theta.
Yeah, sorry, the reason I'm puzzled is this nx iterations without moving forward in time.
Is it incorrect to do so? Like for a given observation, doesn't it make sense to do multiple iterations of, multiple steps towards updating mu x for a given observation?
I mean, yes, you can certainly do that. It's just not how Bayesian filters are usually configured. As you said before, when working generalized coordinates, you can anticipate a moving target. So by the time you've done your update, the target has moved, but you know it's moved. But so you're hopefully spot on, and then you just do a correction and update with the next data. So that would be online data assimilation. To actually stand still in time and iterate around. I'm going to have to think about that. And it's now 15:59. So can I ask you to go back and discuss with your team more revealing simulations of the fluctuations in the precision to use to generate the data that you're trying to invert, and think about plotting the full expectations and posteriors over these slowly varying states, so you can see how quickly it takes for the scheme to recognize something has changed. For example, the lambda, because it takes a little bit of time, depending upon your forgetting and kappa parameters, for the scheme to become increasingly confident and therefore shrink down its confidence, its credible intervals towards the current target, as it were. And then suddenly the target changes, and then it gets uncertain again, and then it should shrink down again to a new level, and then and so on. But so there's going to be two time courses here. The time course of how much data does it require to get a confident estimate of the current lambda, and that will take a finite amount of time. And then how quickly do I notice things have changed? And that will depend upon your betas and your gammas. And your job is to find a sufficient forgetting that allows it not to take, allows it to have sufficiently precise beliefs, which will only accumulate when it's not forgetting, but not too precise that it takes a long time for it to then recognize that things have changed. That's the art here. But to do that, I think you're going to be more, it's going to be easier for you if you have a fast change, perhaps a Gaussian bump function of lambda. And then you can control how the scheduling and the forgetting and the gammas in such a way that you can show that indeed the tracking of the gamma does actually roughly follow, the actual gamma, and then you can then show the posterior estimates of the states and the predicted posterior of the outcomes, and indeed the slow convergence to the parameters. You remember you were saying that the parameters basically don't seem to change at all? Well,
yes,
yeah, yes. That may well be the case. It wouldn't surprise me, but I would be surprised if you didn't see a shrinkage in the confidence intervals as time goes on. So that's the kind, demonstrate the uncertainty quantification that's going on. And then you can talk about all the sort of interesting qualifications, such as regression to the mean and overconfidence problems that you have with variational Bayes, and show how you get this shrinkage when things are more noisy. They tend to shrink towards the prior. You showed that beautifully in the part of the predictive posteriors. When the data were noisy, then things tended to shrink towards zero. That's fully anticipated, an interesting phenomena. There's a principal reason for it, which would be very nice for you to be able to talk about. But to be able to do that, we need to see the full posteriors over all the three sets of unknowns as they evolve in time, under a particular setup that you're in control of, that is just designed to reveal the properties that you want to reveal. And if I were you, I'd just choose one of your the Volterra or the Lorentz system, don't worry about generalizing this. You just want to demonstrate this is the kind of behavior you get when you implement this kind of scheme, and these are the issues. You can then worry about generalizing to all other functional forms, and then worry about structure learning and basic model selection at a later date, and then you can start to, and then, well, we will go through your other questions, but they're all basically questions about structure learning, and they all have clear answers. It's just that we've got no time to give them, and it's your bedtime anyway, so that's good.
Okay, I'll re-listen to this recording, but about this experiment design that you just mentioned, and if I have questions, hopefully I'll be able to ask next week on Monday.
Yes.
Thank you
But
so much, Carl.
Do book a session, a proper methods clinic session with Peter, so that we can focus on the PowerPoints and the questions that you asked. Yeah.
Thank you so much. Thank you.
Earlier in the day. Brilliant. Okay. Thank you very much, everybody. Bye-bye.
Thank you. Thank you, everyone.